And so I'm just showing you the orbital shapes and things that come out of Gaussian. And then we're going to be looking at the selection rules that we have for transitions within the D block. So there's not a whole lot of writing that you need to do today. I'll tell you the important things and I'll say, hey, stop here, write this down. But for the most part, sit back and I would say hopefully enjoy all of this analysis of the D block elements and how these metal ions interact with the environment. Okay, it's pretty simple when you just take two p orbitals that have side-on interaction and end-on interaction. But when you get to the D block elements, now you have 5 different types of orbitals. And they're orbitals that you're not necessarily used to working with. I mean, you've seen them, but you haven't done anything with them. And so that's the point of today, is to do something with those D block orbitals. So here's how they behave in different environments. And really, we can put them in just about any point group on the periodic table, but these are the main 2. When we put a metal in water, dissolve it, a metal cation, the 6 waters will jump onto that metal and form an octahedral complex. And so this is the most common, is the octahedral complex for metals, but there's a lot of tetrahedral complexes too. And so we would take those d orbitals on that metal and put them in either one of these fields. We call these crystal fields. So if they're in a crystal, then it's a solid crystal field. You know, they're surrounded by fixed positions, and the nearest neighbors to that metal are going to either be on the 6 faces of a cube, which would be an octahedral situation, or on the 4 corners of a tetrahedron, which would be a tetrahedral position. And then how do those d orbitals split? Well, the ones that are pointing straight at an element are constrained a little bit. And so the ones that are constrained, typically, because they're constrained, that's like we think of as a smaller box. And so they go up in energy. And the ones that are pointing between the elements, since there's never anything there, especially in a crystal field, like if I'm surrounded by 6 oxygens, if I have an orbital that goes between the oxygens, there's never an atom there because I'm in a crystal. And so that has a little bit more freedom for the electron. And so those energies drop. And so it's still kind of, you can use that particle in a box thinking. If these orbitals are pointing directly at an atom, that constrains the freedom of the electrons and pushes those orbitals up. So we have a 3-2 split. And you can see that's really the biggest difference between the octahedral and tetrahedral, is which one goes up, which one goes down. Either the 3 goes down and the 2 goes up, or vice versa. And that's our D-D splitting, or Jahn-Teller effect. And so this is what we have with these different crystal fields. And so let's go through the d orbitals interacting with hydrogens. You could expand this to interacting with p orbitals too. It would just be even more messy. And so I just did a chromium nucleus or chromium atom surrounded by 6 hydrogens in an octahedral arrangement. And so we're just looking at how all the orbitals mix together. And so here's an example. We've got this. Let me try to draw this as best I can in terms of the cubic nature of this. So we're looking out, and this cube comes down here. So this hydrogen right here is on the face of a cube. So there's a cube that goes around, and it's on the face of a cube. And this one goes over here, and there's this hydrogen is on the face of a cube. And then this hydrogen up here is on the face of the cube. So you see, this is right in the face of those cubes, and the x, y, and z axes come right out of the faces of that cube. So that's how we've set up this arrangement. Okay. And so we have, here's all of the energies of this complex. Now, we're looking at chromium. Look where chromium is up there, okay? It's got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, or really 4s1, and 3d5. So it's got a whole lot of orbitals. And you can see this from this Gaussian calculation, really, really low energy here. That's the chromium 1s, and then the 2s, and then the 2p, and all 3 of those, that's triply degenerate. And then the 3s, and the triply degenerate 3p, And then we start getting into the valence band, the 4s and the 3ds, and that's when it starts mixing with the 1s's. So the 1s orbital for the hydrogen is way up there in energy, and it mixes with the valence electrons on the chromium. It doesn't interact with the 1s or the 2s or the 2p, the 3s or the 3p's at all. And so here's our full molecular orbital diagram for chromium. I've done this to scale now, so you can see that if you want to show that 1s orbital, then it's way down, in energy. So those electrons are pulled very close to that nucleus. Again, the nucleus of chromium has 24 protons. And so those first two electrons are very close. And the closer those two oppositely charged particles get together, the lower energy. And so those 1s electrons are pulled in very close to the nucleus. That's why they're so low in energy. So let's just zoom in up in this region. So if I expand the scale from plus or minus 100,000, then we get this region. And now we can see the 2s and the 2p orbitals. And you see it looks like our traditional arrangement. One orbital for the 2s and then a degenerate set of 3 for the 2p's. Let's zoom in again now, plus or minus 1,000 roughly. And we have the green area. And now we can see the 3s and the 3p's, also not really perturbed. Still a 3s orbital that's distinct and a triply degenerate 3p orbital. But you can see it's we're able to see the valence region now, and it's getting more complicated. So if we zoom in on plus or minus 3,000, we end up with this molecular orbital diagram. Pretty complicated, okay. But we have some singly degenerate, doubly degenerate, and triply degenerate orbitals. So like I was saying, things split 3 and 2 and 2 and 3, that those d orbitals, which were, if we just had the chromium atom, would be 5 equal orbitals, the d squared, z squared minus x squared minus y squared, and the d x squared minus y squared, the dxy, the dxz, and the dyz. So those are the 5 d orbitals would be the same energy, but we put them in this octahedral field and they split 3 to 2, and they interact with those hydrogen 1s orbitals. So let's go through this valence region, and let's go through all of them and see all of the different orbitals that we have in this molecular complex. Okay, this was also just something to give you some encouragement. This stuff gives pretty complex in some of these slides that I've made, and this is a fellow that just out of the blue emailed me, and he said he's studying in Munich, Germany. He saw my videos on YouTube, and he said he took some serious notes for himself. He's taken a few ongoing courses in spectroscopy from MIT and UC Irvine, and my lectures have provided him with a better imagination, information, and satisfaction. So I want you to sort of take that to heart, because a lot of the students, especially the ones that go on to grad school, they get into a more traditional application of spectroscopy, where it's pretty much a full calculus course the whole semester. And no images, no pictures, no analysis of what things are doing. And they struggle with the math, okay? But they tell me over and over again that they know where it's going. So they know that they're going to end up with selection rules. They know they're going to end up with symmetry. They know they're going to end up with whether a transition is allowed or not. But going through the full calculus, like we did in the first 2 weeks, that full calculus gets really involved, and the whole semester is like that in many of these courses. And so I just hopefully you appreciate the visual nature of this course. Okay, so it's nice. All right, so down here, that's the chromium 1s orbital. Again, Millikan symmetry is A1G, point group octahedral. Okay, and the 1s is pulled in so close that on the Gaussian picture, it's inside the ball. So you can't even see it. It's smaller than the ball that they draw for the chromium atom. Then we get to the 2s, and then in the octahedral point group, the s orbitals are A1G, or top row. The p orbitals are T1U, the same as x, y, or z. And now we can see the 2s orbital. We can see it's a little bit bigger than that ball that Gaussian uses for the ball and stick model. And then here are the p orbitals. You can see how small those 2 p orbitals are. They just barely exit the ball. So they're not anywhere close to reaching the hydrogens. And that's another reason why they don't interact, because they're so close to the nucleus, they're pulled in tight, and the hydrogens are so far away. Then the 3s, again, Millikan symmetry A1, the 3 P's, T1U. Now they're getting close. So the 3S is getting close to touching those hydrogens. But you can imagine when we get to the 4S and then the 3Ds, those are going to be surrounding the hydrogens and fully interacting with them. Okay, so now we're in the valence shell. We've put in all our electrons too, so these are all of the occupied orbitals. We have this 4s on the chromium interacting with the 6 1s orbitals on the hydrogen in phase, so they have the same sign. So hopefully you can see this notation here. 4s plus 6 times 1s, that just means that that 4s is in phase with all 6 hydrogens. Everybody understand what we're talking about in terms of this little shorthand? Okay, so let's look at those. Naturally, that's just going to be one complete ball of the same color. Now, it looks like there's something going on inside, and yes, there are internal nodes, like radial nodes, because we're at n equals 4 for the principal quantum number. And remember, n has those radial nodes. Okay, so for an n equals 4, see the 1s would have 0 nodes, the 2s would have 1 node, the 3s would have 2 nodes, and the 4s would have 3 nodes. Yeah, and so this has 3 nodes. Even though we can only see 1, there's 2 even closer in. And then here are the dz squared minus x squared minus y squared orbital on the chromium interacting with the 4 SH. We say it's in phase with all 6, but 2 of those s orbitals are out of phase with the other 4. But anyway, I went ahead and put a plus 6-1s just to say that plus it's in phase with all 6 of them. But do you see that? How that one orbital now can interact with all 6 hydrogens. Normally we see that d orbital with a donut around the middle, but that donut is in phase with those 4 hydrogens. And then this is the x squared minus y squared orbital. So whichever one you want to pick, if you want to say this is x squared, it's out of phase with the y squared. And it's in phase with all 4 of the hydrogens that it's pointed towards. And then those, since it's a 2, these are the only orbitals that point right at the hydrogens. Okay, that's a degenerate pair. Okay, and that symmetry is EG. If you look at the row that has the x squared minus y squared, that row is EG. And then here's the p orbitals that are interacting with the hydrogens. And so there's the px interacting with the 2 hydrogens on the x-axis, the py and the pz, both interacting with 2 hydrogens each. So that's the highest occupied molecular orbital in this particular complex is the T1U. So just to reinforce that, whichever one is the highest one that's occupied, that's the HOMO, the highest occupied molecular orbital, and it's triply degenerate. So it's all 3 of these. Let me pause here with all the occupied orbitals and ask if there are any questions. And so we could verify this with UV photoelectron spectroscopy. We could come in here with UV light and hit it and see electrons come out, and they would come out with different kinetic energies. And the kinetic energy would be the sort of the depth of these orbitals. And so the lower electrons would come out with less kinetic energy, because it's a higher binding energy. It takes more energy to pull them out, and so they would have less kinetic energy. The highest occupied molecular orbital, that electron would come out with the most kinetic energy because it has the least binding energy. So binding energy is kind of how deep they are in the MO diagram. So now you can understand UV photoelectron spectroscopy and X-ray photoelectron spectroscopy. It measures the kinetic energy of those electrons, and that kinetic energy is sort of the opposite of binding energy. And so now we want to look at the other 3D orbitals. You see the 2 of them that were bonding went down here and mixed with the hydrogens. Then we have these 3 up here that go in between the atoms, and they are unoccupied. And so this is the 3D XZ, YZ, and XY. So down there are the d orbitals that bond with the hydrogens, and these are the, I would say, non-bonding, really. They're not touching the hydrogen, so they're not participating in bonding. Not only that, but they're they're not occupied, so they're not doing anything. But if you were to put electrons in them, they wouldn't contribute to a bond or break a bond either, because all of the atoms are along the nodes of these orbitals. All right. And those are the T2G set. And so a lot of times we want to look at the selection rules to see if an electron and an EG, so if light comes in, can it take this electron and excite it up to either one of these levels here or there? So are these D to D transitions allowed? And then we have the antibonding MOs. Let's look at some of those. So now the d orbitals are out of phase with the hydrogens. And you can see that this was the one that was the 2z squared minus x squared minus y squared, and you can kind of see it inside here. It's this little guy right there. You see, here's the lobe on top and on bottom, and here's the donut around. But the donut's been squished into like a little cube because it's in a cubic environment where those hydrogens are pushing on it. So my little picture is pretty ugly, so maybe you can see it better that way. You have the donut on top, the little actual part on top, and then the donut around the middle. So that is out of phase with all 6 hydrogens, and so I show that minus sign. And I put a 2 on here, but I'm going to put a 6. It's out of phase with all 6. And then the other one is the x squared minus y squared, out of phase with the other 4 hydrogens. And so you see how squished it is. And because it's out of phase and it's squished, it's higher in energy. Now, again, this is a really complicated molecular orbital. There would just be 2 electrons in here if it were fully occupied. And you see lots of nodes, and so it has a higher kinetic energy. And then we have those unused p orbitals. I mean, they're filled, but they're not interacting with the d orbitals. And then up here we have the 4p out of phase with the s orbitals. And so you see that the p orbitals have kind of been squished like donuts, and you have this, it's out of phase with the s orbitals. And then that s orbital either in phase with all 6 hydrogens or out of phase with all 6 hydrogens. The hydrogens are kind of squishing that s orbital into a cube. And so here's that cube again. So those are all the orbitals in this octahedral crystal field. Let's look at the selection rules. Are these D to D transitions allowed? So can we go from this EG group to the T2G group? And the reason I ask this is because a lot of times that's whenever we have colored metal solutions in water, everybody says, well, it's the D to D transitions that are causing that absorption. And so here, let's look at the selection rules. So we have this transition dipole moment set up. We have an EG level down here at the bottom. We have the T2G level at top, and light X, Y, or Z, and the octahedral character table is on that T1U row. So T1U times EG gives us T1U plus T2U, and then T2G times these. This gives us this whole huge set, and nowhere in there is the top row of A1G. So this is kind of problematic because we know that these D to D transitions are allowed. So what's going on here? And so what is going on is that maybe at absolute 0 it wouldn't be allowed, but as soon as you vibrate that molecule, and one of those vibrational modes gets up into the first excited level, like let's take a vibrational mode that's in the X direction. If that's excited to the V equals 1 state, that breaks the octahedral symmetry, and then all of these transitions lose their GU character, and boom, you have allowed transitions. And so as soon as something breaks the symmetry, even a little bit, then a lot of these transitions become allowed. So, and so we could have done this very easily and looked and saw an odd number of U's. Okay, and so if you're ever doing this, like on a test, and you see that, you can check your work. I'd still like to see the whole thing multiplied out, but you can check your work to say, and this confirms also that since there's an odd number of U's, we know we're going to end up with a U in the end. Okay. All right, what about the HOMO-LUMO? Now we have T1U as the highest occupied molecular orbital, and then the LUMO is these d orbitals here. Now we have an even set of U's, and so this at least is potentially allowed. All right, and so we have this whole set when you take T1 times T1, and the U times U gives G. And now we take this T2G and multiply it through, and I see a T2G over here, so I know I'm going to get a top row out of this. But I've color-coded it just so we can follow along. T2G times A1G gives this green one. Okay, then T2G times the EG gives that set of two things. Then the light blue ones are T2G times T1G. Still, I get I get an A, but it's an A2, not an A1. But whenever I see anything times itself, like a T2 times a T2, then I know I'm going to end up with that A1G. It has other things in it, but anything times itself is going to give us a top row element. And so since there's an A1 inside this integral, the integral is non-zero. So our HOMO to LUMO transition in this molecule is allowed. And so this is, again, just using molecular orbital theory to symmetry-adapted linear combinations of atomic orbitals, and as they come together, forming these molecular orbitals. Now here's what we get with these coordination complexes. Here's copper and water. You can see now we throw in the oxygen atoms, and it's similar. It's more complicated, but it's similar. You see the oxygen atoms are nestled up to that cation. That makes sense because oxygens have those non-bonded electron pairs. They're going to want to get close to that positive nucleus. And so if you put a cation in water, water snaps to this octahedral complex. Let's look now at a tetrahedral crystal field. We lose the G's and U's, and so now it's much easier to have visible transitions. We don't have to break the symmetry with vibrational excitation. So I picked one that was in a similar position, titanium. The reason I picked titanium is it does prefer tetrahedral complexes, and so a lot of times titanium will be used as an example. So here's the tetrahedral character table, and we've got again this molecular orbital diagram. Those core atomic orbitals are unchanged, so it would look just like the ones that we showed before. So let's go up into the bonding area. Now these little, I don't know what you call these. It's not really like kind of like two horseshoes hooked into each other. It seemed a little strange. Where would we get that shape? And so I wanted to show you the two atomic orbitals that mix in to give us this really strange shape. Now, before I do that, though, let's think about how are we drawing the coordinate system on this tetrahedral complex? Normally, we draw tetrahedral complexes like this, you know, H, Ti, with the hydrogen out front, a hydrogen out back, and one in the plane, right? This is the typical way we'll draw a tetrahedron, but this is if you're going to do the coordinate system, this is a better way. Let me try to draw this. It's a box, and the atoms are on the opposite corners of the box. Can you see it now? See this cube? And so as the octahedral was a cube with the atoms on the faces of the box, a tetrahedron is a cube with the atoms on opposite corners of the box. So this is the back corner and the front corner, and these are the I guess back right and front left. And you could draw the dashed lines if you wanted to show what was going back behind. So that's the tetrahedral field drawn with the coordinates, and the coordinates come out of the faces of these cubes. And so I would say this is probably something that you would want to draw, okay, in your notes if you can. So you see these axes come out of the faces of this cube for a tetrahedral field. And the atoms are on the opposite corners. And so if we took this p orbital that's in the z direction, so this is x, this is y over here, and this is z up here, and we combine this pz with this 3d xy, think of these colors, these lobes of these wave functions as oil and water, okay? So like, let's say the red one's oily and the green one's watery, and we put these together and the water drops can kind of move, right? They can kind of wet each other. And so this red region got together with this red region here and this red region here and made this shape, okay, on top. And the green region here got with those green regions here and made this shape on bottom, okay? And so this is, again, thinking of these as these lobes are flexible and they can sort of merge with each other. Okay, and so then if we can do that with the pz orbital, we can do that with the px orbital, and we can do that with the py orbital. And the reason these can mix is because they have the same symmetry. See, the px, py, and pz have the same symmetry as the xz, xy, and zy. Or, yeah, xz, yz, and xy. So since they have the same symmetry, they can merge together, and that's what allows them to make these strange-looking shapes. When I first saw this, honestly, I looked at it, I was like, where did that come from? I cannot figure this out. And so I had to really sort of chew on how these shapes would come to be. Okay. Here's, again, similar mixing of that PZ and the DXY on the titanium. And this is the non-bonding molecular orbitals. And then we get into some of the ones that are easier to understand. So here's the x squared minus y squared. Again, that's coming out of the face of that cube. So this piece is the x squared piece. And going out of the side of that cube, this piece right here is the y squared piece. And they're opposite sign, which means they're different color. So that's the x squared minus y squared. And then here's the 2z squared minus x squared minus y squared. Again, it's not aimed at any of the elements, so it's not really bonding with the hydrogens. And then here's the 4s orbital out of phase with the hydrogens. And then way up here at the top, we've got the hydrogens out of phase with that py and the dz squared one, so they could either be in phase or out of phase, and here those little donut things are out of phase now. Okay. And so those are all of the molecular orbitals using, again, the minimal basis set. So you might ask, where these orbitals come from? I did a STO3G calculation in Gaussian, and the reason I like that one is because it doesn't add all of the like 5s and 5p orbitals and 4d and 5d orbitals. That just extends the top of your MO diagram, and it's incredibly confusing, and it mixes some of those higher order orbitals down into these lower ones. The downside is the energies that the STO3G calculation gives are not that accurate, but at least the pictures are. So here's our molecular orbital diagram that we get from Gaussian is this HOMO-LUMO Allowed. And so that's a T2 times a T2 times a T2. So we know we're probably going to get an A1 out of one of those pairings, but we'll see. We'll have to do the math just to see if we can get another T2 out of that. And sure enough, the T2 times the T2 gives us this grouping, and then we have a T2 in there. So when we multiply by the third one, we're going to get an A1. So we have the same kind of progression, but it's that T2 times the T2 that gives us an A1. And since there's an A1, which is top row in tetrahedral character table, then we're going to have an allowed. So this is HOMO to LUMO transition is allowed in this molecule. Now, what about the D to D transitions? So we have a T2 to an E. Okay. And so the T2 times T2 gives us an A1, an E, a T1, and a T2. And we see that E in there. So we know now E times E is going to be A1. So again, the other point of this lecture is just to give you more practice with these larger transition dipole moment integrals. And so E times A1 is E. E times E gives us that set which has A1 in it. And then the T1 and the T2 are not as relevant, but I went ahead and did them for you. And you can see now we have top row, so this is allowed. So our D to D transitions are allowed in a tetrahedral point group. It was really that GU symmetry that was causing problems in the octahedral point group. And so this is why we like this. I mean, what we just saw were, examples of the allowed transitions. The gaps in those HOMO to LUMO transitions are in the visible region. And so you just change the nucleus and you get a different color. And so our earliest dyes and pigments were minerals. I mean, if you think about all of these, if you find a chromate mineral, you're going to have oranges and reds and so on, and different clays that you have. And manganese and copper. Copper is blue. It can be green as well if it's oxidized and so on. And so you change slightly the environment of these metals, and you get dramatically different colors. It's really pretty cool. Okay. So all of these, in fact, that's one of the tests for some of these is to put them in solution, dissolve them in acid, and see what the color is. And then you might reduce it and see what the color of the reduced ion is, and you can determine what metal you have, or at least kind of get a feel for what it might be. If it's yellow, it might be iron or it might be chromate. Okay, just the experience would tell you sort of that chromate is a much stronger yellow than the iron. Okay, but again, if you take that iron 3 and you reduce it, putting it with a reducing agent, and it'll go clear. You're going to say, okay, well, chromate wouldn't do that. If I reduce chromate, I get chromium 3, and it gets really dark blue or blue-green. And so you can do some tests that way. So, are there any questions? Because that's pretty much the material that I wanted to cover today. I just wanted to go through those transition dipole moment integrals and show you, at least introduce the idea of a crystal field theory. Okay. All right, so if you have questions, you can come on up.